Okay, so thank you all very much for inviting me here. It's always nice to be able to present your research and get some feedback, especially also in an interdisciplinary forum, so that will be a bit different. Now, when I signed up to do the talk, I was a bit more optimistic about the amount of research time you have as a head of school. I've now realized it's practically zero. So I'm going to talk a little bit less about the mechanisms that I announced in the abstract, and a bit more about the methods of estimation, because it's based on two papers basically. There's a paper where we are proposing to use network analysis to do spatial analysis. So that's what I'm going to present here. And then we apply that then to same-sex marriage, and we are working on a slightly more qualitative paper or mixed methods paper where we go a bit more into the different mechanisms that underlie the diffusion. But that has not progressed all that far. So I am really going to focus a bit more on the methodological side. But since lots of people in Geary do quant anyway, I think that's what we find. So, same-sex marriage diffusion, that's kind of the application that I'm looking at. So same-sex marriage, the first country that adopted it is my home country, the Netherlands, which in 2001 introduced same-sex marriage, legalized it. Norway in 2009 was the first Scandinavian country to introduce it. So it's a relatively recent phenomenon. It's a 21st century phenomenon. And you can see a very clear increase over time internationally. From very few countries that have same-sex marriage to quite a large number of countries where this has been introduced at a pretty much at a global scale. So the black line is same-sex marriage, the green line is civil partnership and same-sex marriage together. And so this really shows a clear example of international policy diffusion, right? So it's one of the more clear-cut examples where you can clearly see that globally a certain policy is basically absent. There's a few early adopters, and then their example gets followed, and you get a significant increase in the number of countries that have this kind of policy. So I think it's a nice clear-cut case study of policy diffusion, and that's why we chose it to then investigate how this method works to estimate. So now there are different mechanisms. Yeah, that's what we're going to explore a bit further in the qualitative paper. For example, in Ireland, it's introduced by referendum. That is actually one of the rarer mechanisms of this being introduced. But so it's a very much popular-driven policy change, where we first had the citizen assembly that suggested that maybe we should hold a referendum. Then a referendum was held, and then this had a much larger support in the whole country than anybody really expected in advance. So there was very strong popular support to introduce this, and the mechanism by which it was introduced is then the referendum. In other countries, it's more back and forth between courts and legislators, referendums pro and against. For example, in Taiwan, there was a referendum that tried to block the introduction of same-sex marriage, as opposed to the opposite, and that won. Right, and in the end, there is a draft bill passed, and so same-sex marriage is introduced in Taiwan. It's the first Asian country to have it introduced, but it took a very different kind of trajectory than in Ireland. Or Hong Kong is an example where it's not yet allowed. There's been also back and forth between the courts, between the legislator. For example, a major case became when one of the Hong Kong citizens had married abroad and then wanted the same rights for his partner or is it her? I'm actually not sure. That this partner would have had had it been a straight marriage. So there's different mechanisms to which this happens, but one thing that is clear from this kind of graph is that these are not independent events, right? So we can clearly see some kind of policy diffusion mechanism taking place. And I think one of the things that makes this kind of furthermore interesting to study is that a lot of the mechanisms that we normally investigate when it comes to policy diffusion don't really apply here. because of the type of diffusion. So we're talking about morality politics, something that's more like a social norm of what is morally acceptable and not acceptable, and how that policy then diffuses internationally. So if you think about why things might diffuse or why spatial clustering occurs, there are these various different theories or mechanisms that we might look at. We might think that countries learn from successful policies abroad or unsuccessful policies abroad and then adapt their policies accordingly, or simply imitate the kind of policies that neighbors implement. Or the yardstick theory is more about voters looking at neighboring states, for example, tax rates in neighbors, and then saying, well, if they get this kind of service for their tax rate, why don't I get the same? So they kind of voters make these kind of comparisons. You can think of norms that just globally become sort of entrenched, like you can think of anti-slavery, for example. Slavery was pretty common worldwide, and then it became worldwide basically not done, right? There's quite a strong consensus that slavery is not acceptable. There's something a bit stronger than this, something where sort of a global norm emerges that is very strong. You can think of, there's some economists in the room. You can think of sort of more economic dynamics, like competition or cooperation, where like different countries might be competing for the same firms and adapt tax rates to keep firms within their country, or certain policies might have spillover effects, where if you have different, say, environmental policies that affect your waters, that will then affect downstream other countries. You might imagine clustering to happen through conditionality, for example, EU membership being associated with certain conditions, and then neighboring countries within Europe to start to get more and more similar policies through conditionality. Maybe the last one is a bit obscure, but you can think of certain cases where states can survive better because, but this is more from the literature on democratization, where the argument is that democracies that are neighboring other democracies have a better survival rate as democracy than democracies that are surrounded by autocratic states, partly because they cooperate more. But these kind of arguments, these last ones, they don't really seem to apply much when it comes to morality politics, right? So they are relevant for tax policies, energy politics, institutions that you develop, and so forth. But so I think it is worthwhile investigating something like same-sex marriage a bit more in depth, exactly because these mechanisms will be very different. The kind of things that will play a role will be very different. So where the project will go after this, basically in the coming months, is to focus a bit more on this aspect and try to see how we can model that in a different way from the other ones and try to crystallize how it focuses on it. But today I'm going to talk more about just sort of the statistical method we use, which is the paper that we had done already. Okay, so first of all, when it comes to same-sex marriage, we don't only see this diffusion pattern over time, where you see a global increase in the adoption of this policy. We also see what, at least at first sight, appears to be a pretty high level of spatial clustering. Yeah, so various countries in Latin America, lots of European countries adopted, not an awful lot of African or Asian countries. So there's a very strong spatial pattern to the adoption of this policy. And so the typical way to look at this is through spatial econometrics. So when we want to study policy diffusion, we talk about a set of nations, a set of states that influence each other. And there are two key features here that are sort of challenges when you look at it statistically. The first is that the dependent variable here is binary. You either allow same-sex marriage or you do not allow. Yeah. So unlike, for example, tax rates or other kinds of policies that might diffuse, that have certain levels, certain rates, most policies are really more binary, right? And so when we talk about policy diffusion, there's often a binary dependent variable. And secondly, there are two types of dependence here. There's a spatial dependence, so neighbors tend to influence each other. And there's temporal dependence, of course. Yeah? So these are not independent observations, but observations where you need to take this interdependence into account. And so one of the models that I've also earlier worked on that is kind of typically proposed is actually not so far, no, it's a relatively small literature still on the binary spatial autoregressive model. So we have an observation mechanism where the dependent variable y is binary, and we assume there's this sort of latent, you can call it a utility function or whatever you want to call it, a latent variable that is continuous, and if it's greater than 0, we assume that we observe a 1, and otherwise we observe a 0. And then we can introduce the spatial effect to this equation. So we have a normal linear relationship between the independent variables and the dependent latent variable. And then here's the spatial effect. So to talk a little bit, I'll get back to this slide in a second, just about this W. So W is then typically just mapping which states border on which states. I mean, you can put any kind of connection matrix. It can be trade relations or similarity in culture or whatever you want to do. But sort of when it comes to just baseline spatial metrics, we are usually talking about which state borders in which state. Yeah, so we can translate a map of countries into a matrix of adjacency. And then we can normalize this typically. Well, I don't know if you call this normalizing, but we change it so that the rows add up to 1 basically. Yeah? So you divide by the number of neighbors. So that if you then pre-multiply a variable with this matrix, you basically get the average of your neighbors on that variable. Or if it's a binary dependent variable, you get the proportion of neighbors that have adopted a certain policy. Yeah? Should I read the Q&A? I've never done a hybrid talk, so this is now a new raising question. How do I see that? My first question relates to whether you have considered using the term marriage equality rather than same-sex marriage. The change really wasn't just about making marriage for same-gender couples legal, but rather about taking sex gender out of the legal equation. Yeah, that's a fair point. So we have been talking about same-sex marriage in the paper mostly, but it's a good point. I will revise the text. So we have this matrix that is the adjacency matrix, and then so this really boils down to looking at the proportion of neighbors that have a particular policy and the effects of this, right? So if a larger proportion of the neighbors adopt the policy, how much more likely are you to adopt the policy?
Sorry, we just have a question from Dave Madden there who wants to know why are the elements on the main diagonal 1 rather than 0?
Oh, they're 0. They're all 0.
Yeah.
Okay, so we have y star on both sides of the equation, so we have to dig it around a bit. And you end up with this what they call using the spatial multiplier. Yeah? So that we can get it on one side. And then there are quite a few estimators in the literature to estimate this equation, which I'm not going to do. That's earlier work I've done. I'm not going to discuss it now. But there are expectation maximization algorithms. There's a Bayesian algorithm. There's a simulated likelihood type model. There are all kinds of models in the literature to try to estimate this equation, to estimate what. And in all of that literature, W is exogenously given, right? So we can put it in other kinds of data. We can put in trade relations or cultural similarity, or etc. But in all of these models, W is exogenous to the model. So there's a few sort of shortfalls to this overall model. The one that I find personally the most important, or one of the most, is that we are talking about spatial interdependence in this underlying utility. But in many cases, I think what we can like we observe is a reaction to actual policies, as opposed to a reaction to how likely another state is to adopt a certain policy. Right? So these utilities, it's a bit different when we look at a time series, where your utility is, of course, something you know or you have inherently the case, right? So we can react to past utilities of ourselves. But it's a bit trickier when we talk about the utilities of neighbors that we don't necessarily observe, right? So one would expect, unlike in time series, one would expect that you really quite often react to the actual outcome of a policy. You react to Y, not to Y star. And there are immediate problems when you start to discretize time in this model. So you can't. So we can't really put. You can't really put Y on this side of the equation, because you can't. You can't sort of rephrase the model when Y is on this side, because Y star would be a function of Y. You can't do this kind of rejigging, right? So the model doesn't work. You can't just put in Y instead of Y star and then go ahead as you want to. It's logically sort of impossible. The second thing is that there are some time series specifications of this hard, but they are very rare and not very well developed. So these models tend to be relatively static. So instead of looking at time, they look at space. But the combination of time and space, there are actually not that many models in this literature. Yeah. Thirdly, where there are dynamic models, they look at discrete point in time. So it's about how do your policies depend on last year's policies or the year before. So it's difficult to model something that happens between t-1 and t. Yeah? So a more sort of nuanced. And there is now a sort of coming up literature that looks at co-evolution, how both W might change as a result of Y, and Y might change as a result of W. But this is largely absent in that literature in spatial, binary spatial models. So the main suggestion we have in the paper is to try to, instead of looking at this binary spatial autoregressive model, which is a systemic way of looking at these diffusion patterns, to switch to network analysis. And what we wanted to do first is to just see if we can more or less replicate this kind of model in this network context. So, I mean, this W matrix is a network, right? So if we make an adjacency matrix of states neighboring other states, we are talking about the network. So this transition from this kind of space to a network is sort of a very immediate step. Yeah? It's just a different visualization. On the right, it's just a visualization of the W matrix. Yeah? But of course, colored by the dependent variable. There are more questions. Huh?
We'll leave questions till the end, because we're recording. That's okay.
Yeah, that's better, because otherwise it's a bit challenging. Oops. Of course, now I don't get rid of it anymore. No?
Close the.
See the on the left.
Oh, yeah. Thank you. I did not see it. Nice. Okay. So instead of using BSAR, I'm using a different model called the stochastic actor-oriented model. Are people familiar with this model or not? Something to talk about. Of course, this is not a model that I've introduced. This is an existing model in network analysis. So people might be familiar with exponential random graph models, which are urgents, which are network models where you try to look at the model as the network as a whole. And you have all kinds of features of that network, how clustered it is, or how dense, or how many triangles there are, and so forth. And then you look at the specifications you have in your data, and you try to come up with those coefficients that start to match those features of the network with the features of your network as an estimation strategy. So in urgent models, which is sort of a more common way of doing this kind of statistical network analysis, much more common than sound, the network is taken as one unit of observation, and then we can compare it. In the stochastic actor-oriented module, the argument is that because we are talking about individuals behaving, or in this case, states behaving, we should be looking at the behaviors at the individual level. Yeah, we should be taking the unit of analysis should be the individual. And so the second assumption here is very much key, that we are assuming that it's individual nodes that decide to make a connection or not make a connection. So imagine a friendship network. We decide who we become friends, right? But the other person has something to say about it. But you get the idea. So if you want to model a friendship network, it might make more sense to not just look at the network as a whole and see what kind of features it has, but look at individual nodes and who is more likely to become friends or less likely to become friends. SAM is a purely longitudinal model, so it looks at changes from one network to the next and how it changes over time. And because, so it's kind of developed from an agent-based modeling perspective. So it is a statistical model, but it's started with thinking like you would think about an agent-based model. And then it started to focus on an agent-based model where we make certain assumptions about behavior and then see how we can fit it to data. And then it became more like a statistical model. So time is modeled here as continuous time. So even though we have observations at discrete time points, t minus 2, t minus 1, t plus 1, etc. The model itself assumes that changes can happen anytime between time periods, and also actors can react to these changes within that time period. So that it's modeled like a continuous time series. The way it's modeled internally is that everything is a mini step. So every step that takes place in this continuous time frame, only one actor can change one time at a time. Yeah. So we can have one time change, and then that might change the probabilities of another time change, and that might change the probabilities of another time change. But there's never massive changes in one point in time. Yeah. So the way it's modeled is in continuous time with small steps each time. Small step being one time change. There's a Markov property, so the modeling of these changes are always based on the current network in continuous time. Yeah? So the only features that affect whether a certain tie gets created or a certain node changes its behavior depends only on the current state of the network and the current behaviors, not on the path to get there. Yeah? Finally, the model is stochastic, so some of these changes will be random. So there are two sort of equations, two functions here that I evaluated. One that affects how often changes take place, because we have this continuous time. So we might have one change between t and t plus 1, or we might have 100 changes between t and t plus 1. So we can model how quickly changes occur. And this can also differ per actor. So there are exogenous variables going into this estimation of the wave function. And then there is the objective function, which determines how you change. Yeah? Whether you create a new tie or not, whether you change your behavior or not. And both functions are based, so the independent variable here are a set of summary statistics. So a summary statistic can be so it can have something to do with how many trials you model, or how many. So I am friends with this person. Now that person is more likely to become friends with me, or how many neighbors have a particular policy. Yeah, that might affect whether I change this policy. Each of these are basically summary statistics. Yeah? So things that are sort of network features. Well, it includes also just things like independent variables. It's also a summary statistic, but they're basically different statistics that one can calculate on an individual node that have something to do with the network structure, or something to do with behaviors of neighbors, or something to do with your behavior, and so on.
Can we ask questions now?
Yeah.
What's in your comment?
I don't mind.
Yeah. So you said independent variable, you would be controlled with independent other things in the model. Maybe you're going to leave this, but I'm interested in what they are, because when I look at that map that you have, And I'm not sure if you're just using spatial or geographically how far you apart, or are you looking at spatial in terms of the system they have? It just looks like the rich countries do it, developing don't do it.
Yeah, so those variables are in the model. That's
So
right.
are you controlling all?
Yes.
So is your the main factor you're looking at is geographical distance?
Well,
Or
adjacency. Yeah, geographical adjacency.
Control the fact that actually these countries are just probably similar as well in terms of
Yeah.
GDP, educational level, political system.
Yes. So in the current, I mean, we get there, but in the current model, we look at geographic adjacency, controlling for things like developments, but also like women in the labor force and a few other variables that we think are relevant. We have only one network specification. So when it comes to these network effects, we are only looking at whether neighboring states have the same policy. We are not. So the extension, part of the extension for the paper that we are developing at the moment is also looking at different networks. And then we can also look at different kind of ties that are also a form of controlling, right? You can think of. So basically at the dyadic level, we don't have any other controls. At the unitary state level, we have other control groups.
If the country is an island, is it adjacent to no one?
I would have to go back to the coding to know for sure. So usually we put a certain maximum distance in there. So,
Well, like you say, Japan is clearly nearer to Korea than Ireland, or it's not technically adjacent. It's not just
that's right. So I think we did adjacency with the threshold of something like I don't know, I forget, 50 kilometers, 100 kilometers. So we don't take out like, you know, a tiny little c and then take it as non-negative. But we look at adjacency, so not proximity. You could also do a distance matrix or something like this. That we didn't. But with smaller c's we take out. Okay. So these statistics. So what you basically can imagine how the model estimates. The model will take the network as it is, calculate all the summary statistics on the network as it is, then take a proposal, like let's make a tie to this particular other agent, look at that second network, calculate all the same summary statistics, and calculate which one fits the data better, right? So it estimates the parameters always on the basis of comparing the current network with one change that is being evaluated, and then try to estimate the likelihood of that. So there are many of these summary statistics, including some very basic ones. So there's also a summary statistic just to introduce independent variables, which I've not outlined here. But there are two that kind of relate to geographic clustering. So these are summary statistics that go into the behavior function. So behavior function means rather than explaining the network, it explains something about the node. And the two that are of some interest is the average alter effect and the next slide, average similarity. So the average alter effect is a summary statistic that looks at network ties. Yeah, so this is for actor I, J, it's W is 1 if it's a neighbor. Yeah. So we basically take the sum of the Y variable for neighbors divided by the sum by the number of neighbors. Yeah. And you multiply this with Y because we're going to calculate two different summary statistics, one where Y is 0, one where Y is 1, and you then compare and try to estimate them. So that's a relatively simple summary statistic to look at how much you are driven by being similar to your neighbors. The second one is a bit more complicated, but seems to somehow work better. So this looks still at these ties. So we're still looking at the sum of the neighbors over the number of neighbors. But rather than looking at whether they have a policy or not, we look at the average similarity between, so how similar in terms of clustering is this particular neighbor relative to the average level of similarity between neighbors. Yeah? So this variable is just is the similarity. So we have a binary dependent variable here. So this can be 1 or 0, this can be 1 or 0. So this is just 0 if they're the same and 1 if they're different. And then 1 minus, which is opposite. Yeah? So this means you have a variable that says that is 1 if they are similar and 0 if they are dissimilar. Yeah? They don't have the same quality. And then we look at the average of the variable across all neighbors, all pairs of neighbors in the whole network. So we get the sort of deviation. Are you more similar to your neighbors than you typically unit out to their neighbors? So you get an average similarity score. Now we had to do a little bit of tricks to make sound work in this case, because as I mentioned, sound is a dynamic time series longitudinal model. BSAR is a static model that looks at one period, and we wanted to compare whether sound works in the BSAR context. Yeah? So we wanted to look at one time period, but it's a longitudinal model, so it doesn't really work. So we tricked it by doing two things. First of all, we copied the same network twice. Yeah? So we create a fake time period by taking the same data. Then we made two changes. I think it's just the first and second observation that was flipped. Yeah? So we just pick two arbitrary observations and flip them. So sound refuses to work if the networks are really the same. But it works if you make a tiny change. Then we fixed that the network itself doesn't change, right? We are talking about a spatial context where it's geographical adjacency. So we are not interested in changing ties. We're not interested in co-evolution here. So we basically fixed all the ties to be the same, because we were interested not in network changes, but in behavior changes. And then we changed behavior, the behavior rate function we also fixed, but we fixed at a high level. So we say to get from this network to this network, there should be many changes. We force there to be many changes. Okay? So what you end up with, you go from a state that is identical to a state in time period data, but we force the model to make many changes to get from A to B. Yeah? So that means that because there are many changes, the initial state becomes pretty much irrelevant. Yeah? Because it's many changes to get here. And so we can estimate to what extent the parameters really explain this outcome, because this becomes largely irrelevant. That's basically what happens. Yeah? So it's sort of a trick to make a time series model estimate a static data. There's a typo. This should have been F0. Yeah? Sorry about that. So this is the result of Monte Carlo analysis we did. So we generate the data using the BSAR model, the spatial autoregressive model. We use that to generate the data. And then we estimate it using both the normal BSAR estimation and using sound. Yeah, so here you see, we have both. Sorry, I should explain that. These two, the first two rows, the data is generated using the binary spatial autoregressive model. The bottom two, the data is generated using sound as a simulation, so rather than an estimate. And then the first is estimated using a Bayesian BSAR model and sound, and the bottom is estimated using a Bayesian BSAR and sound. So in earlier work, I compared all the different estimators for BSAR, and the Bayesian one comes out as one of the best estimators, the Gibbs sample. So that's because it was one of the best ones, we applied it. And so the idea is to, and then for different sample sizes, 50 units, 250 and 500. So the bottom line is that when we have a data generating process that is like a spatial autoregressive model, we can estimate using this sound. Yeah? Of course, we can estimate it slightly better if the data generation process and the model match, but you get pretty close. That's the bottom line. We're not saying that it's better, we're just saying that it's reasonably good. Yeah? Vice versa also works. So when the data is sound generated, you get very good estimates. Yeah? When the sample size is poor, the estimates get poor. we do get, so it's struggling a bit more. So this is negative autocorrelation in the data generation process. This is no autocorrelation in the data generation, and then it goes up 0.1, 0.2, 0.3, 0.5, 0.8. 0.5 and 0.8 are not so relevant because empirically you don't normally observe this much. It's more like something. But this was really, so this is really the bottom line of what we wanted to get at in this simulation study. To show that if you use this network simulation model, but it's based on the sort of agent-based modeling approach and node behavior, you can estimate this kind of static spatial autoregressive model. We also looked at how it does perform in terms of significance tests on the spatial parameter. And so in black is the sound, in gray is the BSAR. BSAR does a little bit better for lower levels of autocorrelation to pick it up as a significant effect. Sound was reasonably low, not as low. Yeah? And if the sample size increases, it gets pretty, it gets pretty close. But if the spatial autocorrelation is low, it still has some difficulty picking. But the advantage is, so the BSAR model is quite restrictive in what you can model in terms of co-evolution, in terms of different types of network effects, in terms of introducing time series and so forth. The sound has all of these things very easily naturally expanded, right? So it's very easy to change the sound model to include co-evolution, to include, we're going to say, other network effects, multiple, etc. Right? So the kind of extensions that are difficult to do with BSAR are very straightforward with sound. So we wanted to show that in the BSAR context, you can use sound, and then sound has much more ability to expand and make the models more interesting. Now, this is the clustering I showed before. So this is kind of the static model. So we can estimate using just probit, ignoring the spatial effect. We can estimate using the BSAR model, or we can estimate using sound. And in all cases, when it comes to same-sex marriage equality, we do get statistically significant effects. So we find statistically significant spatial effects. And we control for population size, employment life expectancy as the more economic variables, and also some variables that have a bit more to do with sort of general, maybe liberal values, female labor force, female seats in parliament, and proportion of Christian and Islam. Yeah?
Is it possible to compare the coefficients models?
That's right. So in the it is, but you have to sort of divide. So there is a fixed ratio to cover. So it doesn't really work perfectly here, but so here we have actually, I forget the exact number now, but we have divided the sound coefficients by a fixed value to get to that. It's because sound is also based on logistic model, and this is based on a probit model, so it's a bit similar to how with logistic and probit, you divide by 1.7, you get from one to the other. It's a bit similar here with sound. But then because we have now the sound model and it's easier to then introduce, say, time series or co-evolution, etc., we can also look at it more dynamically. So this is a map that shows over the whole time period in our data. Well, now we have data from 22. You can see that there's also sort of a gradient, right? So this is an earlier adopter than this, and this is an earlier adopter than this, right? So we see, I'm not going to risk naming countries and get it wrong. But you can see sort of a gradient in the graph. So we then also estimated the dynamic sound model. So we got similar levels. If you take the whole time period and separate observations, and now we don't have to play the same trick with sort of tweaking the matrix, or tweaking these two cases and having these two fake time periods, etc. Now we just have real time periods. We just look at how behavior changes over time. If you put 20 different time points, and then you also start to recover some of these coefficients here, right? So we get a much more similar result, and we can see how we can sort of more dynamically model we have a more dynamic model of the policy diffusion. Now, the other extensions that I have yet to do then have to do with sort of adding more W matrices. So that's going to be the next step. So we want to experiment with migration flows, with similarity in language, similarity in religion. So we haven't done those extensions fully yet. One problem with these is that they all estimate incredibly slow, so it takes forever. But what we have so far is that we do find spatial clustering in marriage equality. Also, when you look at the temporal sequence, so it's not just when you look at the static image of this is what it looks like in 2018. It's if you look at the sequence of the policy diffusion, you see a clear geographic pattern. And that's true when you control for some of these key control variables that we have. And inter alia, we also show that we can use sound in static context if you want to. But then sound offers better opportunities than B-side does to look at dynamics and even to look at how networks might change based on behaviors. So that is not so relevant in the geographic context, but it is in many other contexts. So that's it.